We are starting with section 6.3 and then following it up with 6.5. So you're going to be flipping back and forth between those pages quite a bit. Now the 6.3 part is proving that a quadrilateral is a parallelogram. So as you read through the theorems, read the first theorem on this page, 6.3. What do we conclude? What's the conclusion before we ever look at it on the screen? What's the conclusion of that first theorem? The if part or the then part the conclusion? The then part. So what's the then part say? Then the quadrilateral is a parallelogram. So your conclusion is it's a parallelogram. So write that in. Conclusion of that first one is a parallelogram. Look at the then part in the next one. What's its conclusion? Same thing. And the next one. And the next one. And the next one. So we are concluding whether it's a parallelogram. So these are basically converses of what we did the day before, yesterday, or actually maybe Monday. The hypothesis is a little bit different. The first one is one that we didn't really talk about before. So go back up to that first one. And I think my example is the picture of the hypothesis. If one pair of opposite sides of a quadrilateral are parallel and congruent. So notice in the picture we have a four-sided figure, we have a parallel, or we have a quadrilateral, and we have one pair of sides that are both. You might underline the word parallel and congruent. So they have to be parallel and they have to be the same length. So if you have two parallel segments that are the same length, when you connect the ends of them, you're always going to form a parallelogram. If one pair of opposite sides of a quadrilateral are parallel and congruent, then the quadrilateral is a parallelogram. The other ones are converses of what we did yesterday or Monday. So 6.3.2, if both pair of opposite sides of a quadrilateral are congruent. So as you're marking the hypothesis on the second one, we've got both pair of opposite sides congruent. This theorem is saying that if that's what you have, it's always going to make a parallelogram. I've got some little sticks here I can show you that. I'm going to use the opposite ones the same color. I went red and green. I must be thinking Christmas already. Nice. Okay, so if your opposite sides are congruent, it's making a parallelogram. Doesn't matter what the angle is in between them, as long as those are the same length, you're always creating a parallelogram. It might be a parallelogram that looks more rectangular, but a rectangle is a special kind of parallelogram anyway. So that one does always make a parallelogram. The 6.3.3 is the one about angles. You might underline the word both in these theorems because you've got to have both pair, and congruent. If you only have one pair of opposite angles congruent, that's not enough to know it's a parallelogram. You've got to know if both pair of opposite angles are congruent. So if, in that picture, if we know A and C are congruent and B and D are congruent, we can be confident that that's going to form a parallelogram all the time. And if you think about the 360 total, one pair of these angles would always have to add up to 180. Thinking about those as same side interior angles, you should be able to convince yourself you would have parallels then to go with. All right, two more. On 6.3.4, this is the one about supplements. So if an angle is supplementary to both of its consecutive angles, then it's going to make a parallelogram. Again, this deals with the same side interior angles, converse. So they didn't put numbers. You can put numbers if you want to. We know one angle. Let's say that's 80 degrees. Then the consecutive angles. This one has to be 100. And then consecutive the other way, that one has to be 100. Based on those angles, it's always going to be a parallelogram. Because same side interior angles, it would create the parallels slanted, and it would create the parallels on the top and bottom also. And the last one, if we make diagonals that intersect and actually bisect, so we set up two segments that bisect each other, the ends of those segments will always form a parallelogram. You recognize those as the converses of what we did on Monday. The only one that isn't a converse was that first one. The diagonals bisect each other, then it's a parallelogram. So what kind of questions are we going to be doing in this lesson? A lot of them are going to ask, is this a parallelogram? Yes or no? So we're going to try and support that. Probably one thing we should add to your list, what's something else besides those theorems that will tell us that it's a parallelogram? It's definition. So you might add to the bottom or top of that page so you don't forget about it. Definition of a parallelogram was what? If you don't remember, flip back. Definition of a parallelogram. Where does it give the name parallelogram? Is that definition on the second section, maybe? 6.2. Parallelogram is? Jake? A what? Okay. A four-sided figure, a quadrilateral with two pair of parallel sides. So maybe add that to your list so you don't forget. That's a sixth way that we can verify that something's a parallelogram. Both pair of opposite sides are parallel. Okay, so I think I'm going to look them up by number as we're working with this today. So I'm going to grab me a packet so we have the numbers handy. Everybody got the notes ready? Question? All right, so determine if this quadrilateral must be or is a parallelogram. Justify your answer. Okay, so look at the information that's there. Think about these different theorems and the definition. Does it fit? To conclude, then it's a parallelogram. Think so? Which theorem are you thinking, Henry? 633, do we have both pair of opposite angles congruent? Well, we've got 107, 107. What's this angle?
160.
Yeah, so you'd have to figure out this angle before you could use the first one that you were doing. And you have to be really careful how you find that angle.
So then would 634 work?
634. If an angle of the quadrilateral is supplementary to both consecutive angles, so if I start with the 73 and this 107 are supplements, and then if I go the other way, they're supplements, so yes, that would be the correct one, based on what's there. So yes, it's a parallelogram, 634 is the correct one. Question about my discussion? Okay, how about this one? Parallelogram. If so, what support? Zach, are you saying yes? Which theorem do you think?
Is it
633. Do we have both pair of opposite angles congruent? I see one pair. I don't have both pair.
631 then?
No,
Oh,
it's a no. no. We only have one pair of opposite angles congruent, we don't know enough about the rest of it. So you might, Zach, want to emphasize the word both on that theorem we're trying to use. You gotta have both pair of opposite angles congruent. I know it kind of looks like this angle is the same as this one, but I guess I could slide it one way a little bit further than the other, make it look more like what's called a kite instead of a rhombus. Okay, how about this one? Is there enough there to justify it's a parallelogram? And what theorem or definition do you think it is? Show me what reason you're thinking, Connor.
Well, you could use alternate interior angle.
Okay, what can I get from alternate interior angles?
That the lines are parallel.
Okay, so that would be this one parallel to this one. Would it be the bottom one parallel to the top?
No.
No, because I can't make a Z with the angles that are marked going that way. Okay, so we've got one pair of sides parallel. Is that enough? No, gotta keep going.
If they're parallel, then the other part of the alternate interior angle would be congruent too. But
You mean this one up here?
yeah.
Now be careful, this one's not parallel to that one. And those would be the ones that you have to use when you're forming what you're thinking of. You got stuck, I think. Oh, let's see, it says yes. What was I was just gonna say this one's not possible, but what am I missing? Oh, we can get the triangles congruent. Did you think of that? Okay, we can get the triangles congruent because of that. Yep, reflexive property right there. Angle, angle, side. Same over here, angle, angle, side. So once those triangles are congruent, then we can use all kinds of CPCTCs. So we could get this side congruent to this one, and this side congruent to this one. So I could use, is it 632? Both pair of opposite sides congruent. Okay, kind of tricked myself there for a little while. So we had to really think into that one in order to get them congruent. Okay, and to get it to be a parallelogram. Okay, that one makes sense after we talked about it? All right, let's try another one. Parallelogram, yes or no? I'm seeing a lot of no's. What are you noticing that Hendrik didn't notice yet? Zach?
All the sides.
And they don't all have to be congruent, but which ones need to be?
The opposite ones.
632 says the opposite sides have to be congruent. So it's not the opposite ones that are congruent here. The way that this one is marked, this will be our kite. A kite has congruent segments, but they're the adjacent ones that are congruent instead of the opposite ones. So that one was a no. Okay, another type of problem says show that the quadrilateral is a parallelogram by using the definition of a parallelogram. And it gives us the coordinates. So what's that make you think of? Are you thinking I've got to calculate something? Got to calculate either slope or distance or midpoint. Now, definition of a parallelogram is what? Definition of a parallelogram is both pair of sides parallel. So what can I calculate to determine whether two segments are parallel? Slope, distance, or midpoint? Slope. So I don't have to do all of them, but on this I have to do the slope. And I have to do the slope of the opposite sides. So what would opposite sides be? And I don't know that I would just go by the order they did this, but look at the name. Okay, JL, did you say? JL's a diagonal. Right? JK would be one side, and opposite of it would be LM. JK will be one side, MJ would be opposite of it. If you're not sure which ones are opposites, you can graph it to help yourself know where the points are, okay? But perhaps you even just want to draw one and put the JKLM on it so you know you're doing opposite ones. So I'll show you some calculations. Those are the same points, right? Okay. So the slope of JK, LM, JM, and KL. Wouldn't it be good if you could calculate them that quick? All right, so slope of JK and LM are the same. Do I want same or opposite reciprocals to end up with parallels? Same. So those two have the same slope, so I would be able to say JK and LM are parallel. Notice these two have the same slope, so they would be parallel also. So don't just leave the calculations, but clarify that opposite sides have the same slope, so you have two pair of parallels, something like that. Maybe even say which ones are parallel. Okay, so that was based on which reason? That was the definition of a parallelogram. So if you want to write a note to yourself, when you're doing definition of a parallelogram, you have to do slope. Write that off to the side. Calculate slope in order to use the definition. Okay, here's another one. But this time, we're supposed to use theorem 631. So read 631 and let's think about what we need to calculate. I'm going to just sketch me a parallelogram quick. I know this is not how it's going to look when you graph it, but I'm just calling it ABCD so I can think about it. So what's that first theorem say? If one pair of opposite sides of the quadrilateral are both parallel and congruent. One pair. You pick which pair you want. Should we just, for sake of what we're doing, think the top one and the bottom one? Okay, so to calculate what to determine whether they're parallel? What would you have to calculate to figure out if they're parallel? Slope. So make a note, 631, gotta do slope. But it says parallel and congruent. So what are we gonna have to calculate to see if they're congruent? Distance. So you need slope and distance, but it's not of all sides, it is one pair. Okay, so your note should say one pair calculates slopes and distances. We need the slopes to be the same and we need the distances to be the same. Well, let's see if I've got those calculated for you. Slopes, I did AB and CD. Those were the opposite pair. Now if I chose those, then when I do distance formula, do the same. So you notice they're parallel. Distance of each, they're also congruent. So finish out by clarifying they're parallel, they're congruent, and we did use theorem 631. That make sense? Theorem 635 is the way we're supposed to do it this time. So read 635. What are we going to calculate that would help us determine if the diagonals bisect each other? Okay, midpoint? Okay, midpoint has to do with bisecting, doesn't it? Okay, let's see. This one was K, L, M, N. Okay, midpoint is the correct choice, so make a note, midpoint. What are we doing the midpoint of? The diagonals. We don't want the midpoint of the sides, we want the midpoint of the diagonals. So in your note, put midpoint of diagonals. We want to see if this point is the same on each diagonal, if that cuts each one in half. That's probably the quickest, shortest calculation, because you only have to do two things instead of four. We talked about on the other. So make sure you are picking out LN, L and then N to do one midpoint, and then KM for the other. And here's how it ends up. The midpoint of each one was the same. So that's going to clarify that they bisect each other because that's the common point where they meet. Right. Make sense how you do those problems? Now there are some that tell you the method, there are some that let you choose. And let's just make an agreement. I think I maybe gave you two problems that you get to choose. Choose a different method on each one, just so that you can do more than one type of calculation. All right, there's this type. Show that KLMN is a parallelogram. KLJK is a parallelogram for A equals 3 and B equals 9. What do you think we need to do? Plug those numbers in. All right, there's A plugged in. There's B plugged in. Okay, so what can you tell from those calculated answers? Analyzing, that's the next part in the thinking process. Let's see what's it tell me. Okay, both pair of opposite sides are congruent. It's 34, 34, those two, left and right, are the same, and then the KL and JM. So supporting that it's a parallelogram sounds like theorem 632. So I'm clarifying that to finish it up. Okay. Get the idea that you're kind of doing a proof, but we're not writing it line by line. We're doing more calculation type of proof. All right, so here's when I substitute in. Look and see what I came up with and tell me why it's a parallelogram. Kate, do you know why it's a parallelogram? 634. An angle is supplementary to both consecutive angles. I believe you're right. Because R was 134, consecutive this way was 46, and consecutive the other way was 46. Correct. All right, that section makes sense? Okay, let's look at the rectangle, rhombus, square one. Okay, so flip to section 3 or 6. 5, I think it is. Okay, 6.5 now takes us to the special shapes of rectangle, rhombus, and then even square. So let's do like we did the last one. What's the conclusion of theorem 651? Okay, then it's a rectangle. So conclusion, it's a rectangle. Or parallelogram is a rectangle. 652, conclusion. Rectangle. 653's conclusion. It's a rhombus. It's a rhombus. It's a rhombus. The last three come up with a rhombus. As I want you to look at the hypothesis part, notice that on the if part of each of those, read a few of them, it mentions, like if one angle of a parallelogram is a right angle, if the diagonals of a parallelogram are congruent, you have to know that it's a parallelogram. So you have to get through section 6.3 before you can do 6.5. That's why we're doing them together in the same day. So you might put an asterisk at the top of this page. Must be a parallelogram first. Got to be a parallelogram first, and then the extra things will get it to be more specific shapes. Okay, so 651. If one angle of a parallelogram is a right angle, then it's going to be a rectangle. So your picture, they've got the arrows there to emphasize it's a parallelogram. If one angle is 90, if one angle is a right angle, then it's going to be a rectangle. Why? If you have just one right angle in the parallelogram, why does that make them all 90s?
Because the opposite angles are congruent, and then like
Okay.
the angles across from them have to be supplementary to
The consecutive ones have to be
Yeah.
supplementary. 90-90, 90-90, correct. So you're using some of the things from parallelogram to come up with And the second way to get a parallelogram to be a rectangle is if the diagonals of the parallelogram are congruent. Now that's hard to mark on the picture, that's why they wrote it down below. If you know it's a parallelogram and AC is the very same length as BD, to square it up like that, it's going to be a rectangle all the time. Got your notes? Okay, so we first have to determine whether it's a parallelogram, and then we can talk about this section. So let's do a few samples. Probably have to flip back and forth. A manufacturer builds a mold for a desktop so that AB and CD are the same. BC and DA are the same. And angle ABC is 90 degrees. Why is this a rectangle? Okay, don't start with the page we're on. Flip back. First of all, why is it a parallelogram? Why is it a parallelogram? 632, correct. Then, why is it a rectangle? 651. So this one has two parts to it. 632 and then 651 to come up with it being a rectangle. Okay, rhombus, I didn't put a whole bunch of examples in. The three rhombus theorems. Okay, if one pair of consecutive sides of the parallelogram are congruent, it's going to be a rhombus. So that picture, again, the arrows are there to emphasize it's a parallelogram. One pair of consecutive sides. It doesn't say opposite, it says consecutive. So right next to each other, they've got EF and EH congruent. Now again, we might think, why would just those two end up making them all the same, creating a rhombus? Well, you know it's a parallelogram. So what's true about opposite sides of a parallelogram? They're congruent. So if EH is marked this way and I know it's a parallelogram, FG is going to be the same. Opposite sides in any parallelogram are the same. EF and GH have to be the same also. So just from those first two, you can get all of them congruent. That makes your rhombus. Okay, 654. If the diagonals of a parallelogram are perpendicular, okay, so draw the diagonals in. If they form a 90-degree angle at the middle there, that's always a rhombus. It's going to create a rhombus. And the last one was about the diagonal bisecting the angles. So if one diagonal, so you don't even need both of them, if one diagonal of the parallelogram bisects a pair of opposite angles, so it has to bisect angle F and it has to bisect angle H. Bisect both ends of it. That's going to be a rhombus also. Got your pictures and information? Pretty close. You are finishing up the pictures. So if you want names for these, probably a lot of them could be converse of whatever we called the related one before. Okay, looks like we're ready. Okay, and I guess just a reminder, you can use the definitions of rectangle, rhombus, or square. So again, you might put a note on that page. Remember definitions. And as I put up here, the definitions sometimes are easier because you don't have to get it to be a parallelogram when you use the definition. All right, the directions here say determine if the conclusion is valid. So is it correct? Is it valid to determine that this is a rectangle based upon what we're given? Okay, if not, tell additional information that we would need. Okay, let's try and mark this up a little bit. Angle ABC is a right angle. BCD is a right angle. CDA is a right angle. Is that enough to conclude it's a rectangle? So now let's think about things we know. Hendrik, you're saying yes? Giving me some numbers to follow? Looking for it.
Would that be 6, 5, 1?
Can't use the 5s until you do the 3s. So flip back to 3 first if you want to use that.
Could it be 6, 3, 4?
Exactly. We have an angle supplementary to both consecutive angles. So it is a parallelogram. Now which 5 did you want?
6, 5, 1.
6, 5, 1, because we have one angle, we have actually 3. One angle in that is a right angle. So correct, but you had to do both. Now you probably could have done the definition. If you would use the 360 total and subtract to figure out angle A as 90, you would have all angles congruent, and that's what our definition was. All angles, right angles, something like that. Okay. EF congruent to FG, EG, and FH perpendicular. Okay. Is that a rhombus? The rhombus. Hendrik's saying yes. You guys are saying no? No. Which one are you thinking?
First, I was thinking 6, 5, 3, but you
Can't-
gotta use the.
Yeah, you gotta use the 3s before you
So I
can go
was
to the
looking-
5s. So he was looking for something from the 5s. Is there one that fits? Unless I tricked myself, I'm thinking no. And that one did not have enough to get the 5 3s. I mentioned a couple things in the 6 5s, but we can't do that until we get the 6 3 figured out. So that one was not valid. How about EB congruent to BG, FB congruent to BH, EG, so this whole diagonal is the same as that whole diagonal. Should I change some markings then? Because based on my markings, does it show that EG is the same length as FH? Not really. They would actually end up all being the same. And then triangle EBF. This triangle is congruent to EBH, this one. So we probably can do a lot of CPCTC things. We could do this side congruent to this one, this angle congruent to that one, and that one, and that one. These two angles congruent, which would mean, would that mean 90 and 90? How do I know they're congruent? They had to match in these congruent triangles. Is that giving us enough? We're trying to come up with it being a square. How do we do that? We're going to have theorems about squares. What do we need to think of? Anthony, fill me in. To get a square, can we use any of these theorems to get a square? You got something you wanted to say? How can we get a square? Squares and rectangles are the same thing, kind of. If the rectangle has all sides equal, which means rhombus has to be entered into it. So to get a square, you have to get first a parallelogram, and then a rectangle, and a rhombus. All right, so we've got a lot of thinking. Okay, let's see if we can first come up with parallelogram. Left-hand is falling over there.
No, I wasn't.
All right, is this a parallelogram? Can we come up with something on the 6.3 page or the definition that would get it to be a parallelogram? 6.3.5, diagonals bisect each other. Yes. Okay, so we know it's a parallelogram. I'll make a note. 6.3.5. Okay. Is it a rectangle? Which one? 6.5.2. 6.5.2, diagonals of the parallelogram are congruent. Yeah, that's what this told me, right? They were congruent. So I do know it's a rectangle. 6.5.2. 6.5.4, the diagonals of the parallelogram are perpendicular. Okay, so that gives me the rhombus. So is it a square? Yes, because we have both rectangle and rhombus figured out. So yes, it's valid to come up with a square. So you're not doing a lot of calculating probably in this lesson, but you're doing a lot of analyzing to determine whether something is the correct conclusion or not. All right, let me just click through some here and make sure that there aren't some real significant things that I'm forgetting for the lesson, and then we'll get to our quiz. Okay, I think I probably had, okay, you have to do some calculating. Oh, look at the directions here. Use the diagonals to determine whether the parallelogram with these vertices is a rectangle, rhombus, or square. So they've already told you it's a parallelogram. So you don't have to worry about the 6.3 page. But what are you going to calculate on the diagonals? What can you calculate to tell you whether it's a rectangle based on the diagonals? What has to be true about the diagonals for a rectangle? They have to be congruent. So what do you calculate? Length, distance formula. Okay, so distance formula on the diagonals would tell us rectangle. Rhombus. What's true about the diagonals of a rhombus? Through your notes here. 6.5.4 says the diagonals have to be perpendicular. So what would we calculate? Let's see if they're perpendicular. Slope of the diagonals, not the sides. Okay? And then square, if it passes both of those, then it's going to be a square. So again, some of those same formulas. Hopefully we're getting good at those soon. And so here were the calculations. The two diagonals were the same length, so it's a rectangle. The slopes are opposite sign and reciprocals, so it's a rhombus, which would mean it's a square. I think I had a second one. Let's look at the calculations. That's how long the diagonals are. Not the same. So that means I've eliminated what shape or shapes. Can't be a rectangle. And if it's not a rectangle, can't be a square either. So our only possibility is rhombus or nothing. So let's see. Rhombus, slopes, opposite sign and reciprocals. Yep. So it is a rhombus. Oops, I went too fast, but that was a rhombus. Understand the calculations and analyzing? All right, let's write down what the assignment is based on those sections.